Okay, so we are doing lesson 73 today. Today we're actually going to do a hypothesis test the whole way through. So we're going to state our hypotheses, actually calculate whether or not we have convincing evidence, and make a statement about a claim. So before we get into that, I'm just going to briefly touch on what we talked about last time. So last time we were introduced to this idea of having a claim that we want to find evidence against. So our first one was the basketball player that claims he can make 80%. And we used that to go into how we state hypotheses for a test. So we can have a one-sided test or two-sided test, and we're going to see both of those today in our examples. Once you have your hypotheses, you can find if you have convincing evidence against the claim. So to find convincing evidence against the claim, we use a probability, and we now know that that probability is called a p-value. And how we know if that p-value is enough convincing evidence is by comparing it to a significance level. And that's the last thing that we left off with, is comparing our p-value to our significance level and deciding if we should reject or fail to reject the null. I had a couple of questions last class period about number 3 on the ones that you guys were supposed to do on your own. And number 3 doesn't give you your significance level. So if a problem doesn't give you a significance level, and you'll see this today, you use alpha is 5%. So you use alpha equals 0.05. So if they don't give you significance level, you use 5%. So she was asking, okay, do I use this alpha, and then wanted to double check what answer it would be. And when I was helping her double check, I still need to say, if the p-value is low, reject the hoe, because there's so many numbers in these problems that it's hard even for me to decide, do I reject or fail to reject? So remember, we have that saying to help us if we need it. So that then leads into tests for a proportion. So today, everything we're doing is for P, a proportion. Nothing today will be a mean. Everything will be proportion. So confidence intervals and significance tests are based off of the sampling distribution of our statistic. So that is, both use probability to say what would happen if we did the inference that we're doing many times. So because of that, we have to check conditions. Because we're working with a sampling distribution, which relies on you doing a method many, many times, we have to check conditions much like we've done in the past 2 units. That's the good news and the bad news. So the good news is these conditions are the same conditions we've been testing for 2 units now. The bad news is these conditions aren't at least my favorite thing to be checking. So we have to continue on with checking the conditions. This will allow us to decide if we can carry out our test. So just to remind you of our conditions, the first one is randomness. We have to make sure that our sample was random. If it's not random, then our sample probably doesn't reflect the population, which will cause issues. So first one is the same as always, randomness. Second one is large counts. The second one is large counts. And it enables us to use a normal curve to find a probability. So we use or we have the random condition to verify that our sample truly matches the population. We have to check large counts so that we know that we can use this Z table to find our probability. And then the last one is that we need to check the 10% condition, which allows us to calculate our standard deviation. So our three conditions: randomness, large counts, 10%. Randomness says that we can infer about the population. Large counts allows us to use our Z table. 10% allows us to find standard deviation. So there's three more reminders before we actually look at calculating a p-value. So this says, remember, a significance test uses sample data to measure the strength of evidence against HO in favor of HA. So what we do today, everything is based off of sample data. So if I refer back to our basketball problem, if we have our basketball player that claims he can shoot 80, if we have him do that and he only makes 40% of his shots, that to us, just by looking at the sample value, is pretty strong evidence. Like, that's very far below 80%. But if he shoots 76%, we don't know. That's below 80, but is it too far below? That's what the sample data is going to help us figure out. We're going to use that sample data of 76% and mathematically decide, is that too far away? Now, we did a hypothesis list or state the hypothesis for a pineapple problem, and you don't have to go there, but on page 702, we talked about how this pineapple company changes the way that it changes the way that it irrigates its crops. We would not be able to actually carry out this test unless they took a sample of these new pineapples and weighed them. So we can only do a significance test if we have sample data. We use that to find a test statistic. So our reminders before we find these are, the test compares your sample statistics, so p hat or x bar, from sample data with the value of the null hypothesis. So we're comparing our sample value to the null value. So we would compare him making 40% of his shots to him claiming he can make 80%. Values of the statistic that are far from the null parameter value gives strong evidence against the null. So this is what I was referring to when I said, if he shoots and only makes 40%, that is very far from 80%. So that would be strong evidence. Well, how do we know how much is far? How do we know when it's too far? Well, to assess how far the statistic is, we have to standardize it. And this is what we learned in Unit 2, Unit 3, one of them units. I don't remember which one. We're going to standardize our sample value, which means we're going to figure out how far away from the mean or the true value it really is. This is our formula. Where it says test statistic, that's really Z. I'm just trying to find a color. This is really Z. So our test statistic is going to be Z. our statistic is p hat. Our parameter is p. And our standard deviation is sigma sub p hat. And that sigma sub p hat is the formulas on the third bullet. So our formula for this is right here. Okay, so we're going to figure out how far our sample data is from the true value. So the test statistic says how far the sample result is from the null parameter. I'm going to highlight that as soon as I find a color. You can use this test statistic to find the p-value. So we're going to standardize it to say how far away from the true value is it, and then we're going to find the p-value based off of that. So our first problem says, according to the U.S. Census Bureau, the proportion of students in high school who have a part-time job is 25%. So I'm going to highlight that. That's our first important value. An administrator at a local high school suspects that the proportion of students at her school who have a part-time job is less than the national figure. So our counselor thinks that it is less, or our administrator. So less than the national figure. She then selects a random sample of 200 students and finds that 39 of them have a part-time job. So this says calculate z and find the p-value, and it also wants us to show what that would look like under a normal curve. So I'm going to state my hypotheses just so that it's clear what we're doing. My null hypothesis is that the true proportion is 25%. And that's the null because that's what the Census Bureau calculated. The alternative is what the administrator thinks. So the administrator thinks that it's really less than that for her school. So less than 0.25. One reminder here is that we always use the same value for the null and the alternative. It's the symbol that changes. Then we have to define p, where p is the proportion of students in high school who have a part-time job. So this was not required for us to do this problem. We did not have to state the null and alternative, but I think it's helpful in finding your p-value. So I wrote that out to the side so that I could do my test to the right. I could carry out and find all my test values. So if I have to use this formula to find my test statistic, I need to know what p hat is. So p hat is equal to 39 out of 200. She sampled 200 students and 39 of them had a part-time job. We change this to a percent. Hi. She's right here. So that gives us 195.195. Is that what you guys got? Yeah?
Thank you.
You're welcome. Okay, now we're going to find Z. And it's going to be a big old fraction. It's going to be big fraction. So for Z, we take our sample value that we just calculated, 0.195. And we subtract the value of P from the null hypothesis. So 0.25. Then we got to divide that by sigma sub P hat, which is the big ol' radical. That formula says I take the P from the null, 0.25, times 1 minus P, that's 0.75, divided by 200. I plug that in, and that's going to give me a Z value. So I plug it in exactly like that, which means that I have to type green button Y equals, and make a fraction, 0.195 minus 0.25, arrow down, hit your alpha green button, and Y equals, oh, I lied, hit clear. Hit your blue button and your X squared button to get your radical. Then do green to get your fraction. So I have it in my calculator exactly like it is on my paper, and I get negative 1.796. Well, if I just take a quick glance at my Z table, it reminds me that I can only go or only need 2 decimals after, or 2 places after the decimal. So I'm going to round this up to negative 1.80. So that's the Z that I'm actually going to use. So what this means is our sample value is 1.8 standard deviations below the national figure. We're 1.8 standard deviations below. So that's kind of far away. To show that on a normal curve, here's what we just found. So we're going to draw our normal curve. And when we're working with our Z table, the center is 0. And we go out 3 standard deviations on either side. So our sample value is at negative 180. So that's where I'm going to draw my flag. This matches a P hat of 195, of 19.5%. We are 1.8 standard deviations below the center, which is the claimed value of 25%. They are asking us, what is the probability that we would get a sample this low or lower? How do I know we're going lower? Because my alternative has a less than. So we're finding this area from our normal curve. So I know to color in to the left because my null hypothesis is pointing, or sorry, my alternative is pointing toward the left. So if I go to my z-table, I go down to negative 1.8 and over to the 0 place. So 0.359. So here's how we write this out. Our p-value is equal to the probability that z is less than negative 180. Why? Because that's the same as the probability of getting the sample that we got or lower. So getting the sample that we got or lower. That was 0.0359. So the probability that we would have gotten a sample this low if her school matches the national figure is only 3%. Well, 3.6%. So this would be, in most cases, considered strong evidence. In this case, at alpha equals 0.05, we would reject the null. We have convincing evidence that at this school, the proportion of high school students is less than the claimed national figure. We're hanging in? Okay, so we find our z value, we draw a curve. So that's the part where we calculate the test statistic. Now we got to go in and do the whole thing. So we got to check the conditions, state the hypotheses, do all the things. So that's on page 709. And this process is called the state plan do conclude process. So on each of these pages moving forward, each of them have listed state plan do conclude for you, just to remind you that that is the method that we're following. So all the next 3 pages will have this state plan do conclude. So a potato chip producer and its main suppliers agree that each shipment of potatoes must meet certain quality standards. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load. So our value is 8%. If it has less than 8%, then we keep the entire truckload and use it to make potato chips. To make the decision, the supervisor will inspect a random sample of 500 potatoes from the truck. The inspection reveals that 47 of the potatoes have blemishes. We must carry out a significance test at alpha equals 5%. So the alpha that they want us to use is 5%. And the question that we're answering is, should we reject the shipment or keep the shipment? Okay, so I'm going to do just a smidge of highlighting before I start. Okay, so these next three problems are set up to be exactly how you would answer these on a free response question. So state what we want to do. We want to perform a significance test at alpha equals 0.05. So we want to do a significance test at alpha equals 5% using the hypotheses HO is that P is equal to 8%. Really, we want it to be less than 8, but when we do a null hypothesis, we always use an equal. So we're just going to say equal to 8%. The alternative that we're checking for is that P is really greater than 8%. And the reason that we're doing greater than is because that's how they frame the problem. They say if there's more than 8%, we send it away. They don't frame this problem as if the blemishes are less than 8, we keep the shipment. They frame it as if it's more than 8, we send it away. So we go with more than 8. Over here, we have to define our parameters. So where P is the proportion of potatoes in the truckload that have blemishes. So we're testing whether the proportion is equal to 8% or really greater than 8%. Our plan is that we want to do a one sample Z test for P. So last time what we calculated was a one sample Z interval. This time we're doing a Z test. It's a Z test because we have to use our Z table to find the probability. Before we can actually run this test, we need to check our three conditions that we're hopefully getting used to checking. So first one that I check is that we took a random sample. So we can say a random sample of N equals 500 potatoes was taken. So a random sample was taken. Next, I would usually check large counts, but for some reason I switched them. So, and it's okay, it doesn't matter what order you check them in, but on the previous page it's randomness, large counts 10%, so these are flipped, but that's okay. N is all potatoes in the truckload. And I believe that we're talking like a semi-truck. So there's like thousands and thousands of potatoes in the truck probably. It's like when somebody wants you to guess the M&Ms in a jar and it turns out there's like 10,000 in there because you can actually fit a lot of M&Ms in a jar. It's that situation. So if it's all potatoes in the truckload, it's reasonable that 500 is less than a tenth of that. It's reasonable that 500 is less than a tenth of that. And then our last one is the 10% condition. And one thing to notice here is that it says, assuming the null is true. So that's why these P's have a little sub-zero on them, because it's the P from the null hypothesis. So assuming the null is true, N times P is 500 times 8%. And that equals 40. I'm pretty sure. N times 1 minus P from the null is 500 times 92%, which is 460, I believe. And this tells us that we can use the normal distribution now. So this large counts tells us we can use the normal distribution. So now our last step is the do portion, and that's exactly what we did here. The do portion is this part. So we need to know P hat, because we know P from the null and we know sample size. So what we need to have here is P hat. Our sample of 500 potatoes had 47 with blemishes. That is the percent 0.094, so 9.4%. Then we can move here to calculate our Z. So right after this formula, which you don't have to write. You don't have to write this P hat minus P sub 0. That's just here for your reference. Is our sample value, subtract the null proportion, which is 8%. We're going to divide that by the big old root. So we remember we use our null value for P. So we're doing 8% times 92% divided by our sample size of 500. And I'm going to make a note to myself that this is the only place I use P hat. This calculation is the only place that we use P hat. We don't use it anywhere else in this entire problem. Okay, practice plugging that in, because lots of people had trouble plugging in stuff on the last exam. I'm going to give you like 45 seconds. About 10. Okay, I got 1.15. Is that what you guys got? So our sample is 1.15 standard deviations above the claimed value. That's not too far away. Let's see what p-value that ends up giving us. So what that looks like in terms of a normal curve. Zero's in the center. Our sample value ended up being at 1.15. That matches our actual sample proportion of 9.4%. So this is 1.15 standard deviations away from the claimed value of 8%. This time we're testing what's the chances we would get a sample value that big or bigger. How do I know I'm going bigger? Because it's pointing toward the right. So this time I'm filling in this part of my normal curve. I'm finding the area to the right because my inequality is pointing toward the right. So my p-value is the probability of z being greater than 1.15, which is the probability we would get a sample value of 8% or higher. Just kidding. 0.094%, because that was our sample value. So to find this, remember, if it's the area to the right, we have to do 1 minus. So we do 1 minus, we go to our table, 1.1, slide over to the 5, and I get 8749. So this gives us to the left, and that's why we're minusing it from 1. So 1 minus 8749 gives us a p-value of 1251. 0.1251. So that's 12.5%. So what we just found is the probability that we would get the sample that we got if there really is only 8% blemished on our shipment is 12%, which is actually pretty high for a significance test. So to make our conclusion, we have to follow the framework that they gave us a tip on, page 706. There's 3 things that we have to make sure that we address. So the first one is explicitly compare p-value to alpha, make a decision whether to reject or fail to reject, and then use context. So explicitly compare our p-value. Since the p-value is 0.1251, since the p-value is greater than our alpha of 5%. That's our explicit comparison. because our p-value is greater than our alpha, we fail to reject the null. You could also say HO instead of the null if you prefer. So the p-value here is not low. The p-value is high. So we failed to reject. So this was 1, explicitly compare. 2, say we fail to reject or we reject. And then 3, use context. There is not convincing evidence that the shipment contains more than 8% blemished potatoes. So the producer will use this truckload or keep this truckload. There's one more exam tip down here, and this one says, when you get this conclusion, when you fail to reject, be sure that you never say anything close to the null is true. So right here toward the end of this little box, it says, saying anything that sounds like you believe HO is true or might be true will lead to a loss of points. We say that we fail to reject and say there's not convincing evidence. We don't say we fail to reject the null. The null is true, or we have evidence for the null. You don't want to say anything like that. Okay, so next one is very similar. So we had one about potatoes. Oh boy. Now we have the one from the campaign to prevent teen pregnancy and unplanned pregnancy. So, according to this national campaign, 20% of teens aged 13 to 19 say they have electronically sent or posted sexually suggested images of themselves. So that is our null value, that P is 20%. The counselor at a large high school worries that the average or the actual figure might be higher at her school. So she's worried that at her school it's actually more than 20%. To find out, she administers an anonymous survey to a random sample of 250 of the school's 2,800 students. All 250 respond, and 63 admit to sending or posting sexual images. Carry out a significance test at alpha is 5%. What conclusion should the counselor draw? Okay, so this starts out exactly the same as the last one. We want to perform a significance test. You could also call it a hypothesis test. At alpha equals 5%. Now you guys write the null and the alternative. Take like 1 minute and you guys write what you think HO and HA is. You don't have to define P. Just make your null and alternative. about 30. $10. Okay, so your null is that the true proportion at her school is 20%. The alternative is that it's really more than that. And I wanted to add in a note here. Remember that your null and alternative always have the same number. What changes is your inequality or your equals. So P is always equals, or the null, I should say, is always equals. The alternative will be an inequality, but the number will be the same. So down here, I define P for us because this one is really, really long. So where P is the true proportion of all teens aged 13 to 19 at the school who will say they have electronically sent or posted sexually suggestive images of themselves. Okay, our plan. So remember, in all of these, we're going to get our state, plan, do, conclude. So our plan this time is the same as last. We want to run a one sample z-test for P. And we've got some conditions that we need to check in order to do that. So first one is randomness. A random sample of n equals 250 students was taken. So a random sample was taken. In this problem, they actually give us n. What is the population size? Perfect. N is 2,800 students. 10% of that is 280. So 250 is less than or equal to 1/10 n. Notice there I didn't add in for us, so it's reasonable to assume, because we know for sure that 250 is less than or equal to 280. For our large counts, notice that we start again with assuming the null is true. N times P would be 250 times 0.20. I think that's 50. Is that true? Which means that this one is 200. Have you guys noticed that these two numbers always add to the sample size? 50 and 200 is 250. So we're good to use our Z table. Okay, because this is exactly like the last one, I'm going to freeze the last one on my screen and have you guys try just the do for this problem. You obviously don't need to write in this thing that I have highlighted in pink, but everything else you need to have. If you want to try the conclude, you can, but I'm only expecting you to do the do. not the Mountain Dew. If you're at home, I'm going to pause the video so you pause and do the problem and then unpause when you're ready. Okay, so I got a p-value of 0.0197. So your sample value is 0.252. Your matching Z should be 2.06, which leaves you with that p-value. How'd you guys do? Did you get it? Okay. Now our conclusion is basically the same. The first sentence is always the same. So we say since the p-value, then we give our p-value is less than. This time our p-value is low. So 0.0197 is less than our alpha of 5. We reject HO. So we reject that at this school, 20% of students have electronically sent or posted images. There is convincing evidence that more than 20% of teens aged 13 to 19 in her school will say that they have electronically sent or posted sexually suggestive images of themselves. The reason that we're saying we have convincing evidence that more than 20% do this is because that's our alternative. And the convincing evidence is that if it truly were 20%, the chances she would have gotten a sample this high are 2%. So 2% is way too low. That must mean that at her school it's higher. You're hanging in? Okay, the last one is slightly different. The method is the same. There's just a few slight differences. So, according to the Centers for Disease Control and Prevention, so the CDC, 50% of high school students have never smoked a cigarette. Okay, so that is our claimed proportion. Ava wonders whether this national result holds true at her large urban high school. That is the second piece of information we need. She wonders whether it holds true. For her AP Statistics class project, Ava surveys an SRS of 150 students from her school. She gets responses from all of them, and 90 say they have never smoked a cigarette. What should Ava conclude? Give the appropriate evidence to support your answer. So they're asking us to perform a hypothesis test. So we want to perform a significance test using the hypotheses. The null is that the proportion matches the CDC, 50%. Ava wonders if this holds true for her school. So Ava is not specifically saying she thinks it's less than. She's not specifically saying she thinks it's more than. She's just saying she wonders if it's true, which means that our alternative is a two-sided test or a two-sided alternative hypothesis. We're testing that it's not 50%. So it could be more, it could be less. P in this case is the proportion of students at Ava's school who will say they have never smoked cigarettes. Now this next part is really important. No significance level was stated. So we will use alpha is 5%. So we will use the standard 5%. Okay, what's our plan? Same plan as before. We're doing a 1 sample Z test for P. So everything we're doing today is a proportion. First one is randomness. An SRS of N equals 150 students was taken. N, so I wanted to give you a little bit of guidance on this one. N is all students at Ava's large high school. So the key here is that the prompt tells you she goes to a large urban high school. So it is reasonable that 150 is less than 1/10 of the students at her school. We would be considered a large high school, and we have about 3,000 students. Okay, I want you to try the rest only to the Z. So you'll get a Z value here and then stop. So check your your large counts, find your P hat, use that to find your Z, and then we'll check back in to draw the normal curve together. Okay, I have a Z of 2.45. So I check my conditions up here. I got a Z of 2.45. So I've started my normal curve. Just going to finish up now. And then I am going to plant my flag at 2.45 because that is what my sample gave me. So my sample of 60% that have never smoked a cigarette is 2.45 standard deviations away from the CDC's claim of 50%. So we are finding the probability of getting a sample this high or higher, but this is a two-tailed test, which means that we're not just looking to see if it's greater than, so the sample we got, or higher. It could also be lower. But remember, we have to use our sample data. So what we do is we take this Z value and we use its mirror. So we plant another flag at negative 245. We don't list a sample value that would match that. We just list that we would take our sample value, this part that I have shaded in here is the probability I would get the sample that I got or more. This probability is that I would get the sample value that I got or less. So as big or bigger than my sample, as small or smaller than my sample. So this takes care of if it's greater than 50, this takes care of if it's less than 50. Does that make a little bit of sense? If this would have been on the negative side, you just reflect it to the positive side. So you use the sample that you get, and then you reflect it to find the other tail. So in this case, finding our negative one is easier because it's the value to the left. So I don't have to do a 1 minus here. So I go to negative 245 and get 0.0071. So my p-value, in this case, I don't really have a nice statement for it. I mean, I could write out, it's the probability of z less than plus the probability of z greater than. That's just too much, in my opinion. So we're just going to write p-value is 0.0071. And if that's this area, then that's also this area, because this curve is symmetric. It's exactly the same on the left as it is on the right. So plus 0.0071. This gives us a p-value of 0.0142. So 1.42%. What we found is that if our school matches the CDC, the chances we would have gotten this sample are very, very low. So that must mean that we don't match the CDC's value. So since the p-value of 0.0142 is less than alpha of 0.5, and it's not always going to be 0.5, so or 0.05, sorry. Be careful about that. Be careful about your alpha, because it won't always be 5%. P-value is low, so we reject the HO. So reject HO, or you could literally write reject the HO. There is convincing evidence that the proportion of all students at Ava School who will say they never smoked differs from the national result of 50. Maybe I should just write 50 there, not P. So we don't have evidence that it's more. We don't have evidence that it's less. We just have evidence that it differs. Okay, so all that's left is your check for understanding. So the ones that you're supposed to do on your own. So on number 39, these numbers are crazy because they match your book. So if you looked at chapter 9, number 39 in your book, this would match that problem. This is a sample survey about whether students are satisfied with the parking at Cypress High School. So they make a change to the parking, and the principal wants to know if the change was effective. So this sentence here where it says that the principal wants to know if the change was effective tells you what your alternative should be. So if we start with 37% of students being satisfied with the parking, and we're trying to change it so that more students are satisfied, our alternative is greater than if the change was effective. More students would be satisfied. Does that make sense? You're sure? Okay. 2 should be fine. Hop to number 3, which is 43 bullies in school. This problem is a correct the error problem. So this is the significance test, and a lot of it is wrong. Like, there is a ton of mistakes. This problem wants you to go through and highlight the errors, then fix them. So what I recommend to you is that down here in the blank spot, you run the hypothesis test on your own. So do the whole thing and then come back up and compare what you have to what they have. I promise you it'll be easier to spot the mistakes if you know what it should look like and you compare that to the bad one. You can do it whichever way you want, but I personally think that's the easier way. Are we okay there? So this is your homework, these 3 problems: 39, 46, 43. I don't know why those are out of order, but what else? Okay.